Good. So we left at the independence test. This is one of the NIST tests. So let x1 up to xn be a sequence with IID variables, independent and identically distributed variables. And suppose that the expectation is mu, the probability that the variables are equal to mu is 0, and the variables are symmetric. Probability that xi is larger than mu is 1/2, and probability that xi is less than mu is also 1/2. Then, if we take n, capital N with the subscript n, as the number of blocks not crossing mu, then the mn has asymptotically, for large n, the normal distribution n with parameters n plus 1 over 2 and n minus 1 over 4. Now, what we can do is take this number, the number of blocks which do not cross mu in the sequence, subtract the expectation, divide by square root of the variance. So we take this, subtract this, divide by square root of this. We can even simplify it a bit and use this as the test statistic for testing independence. Does not work that well. If we take t being nn minus n plus 1 over 2 over square root of n minus 1 over 4, then t has asymptotically the standard normal distribution, and we reject the null hypothesis of independence whenever this test statistic is too large, meaning that it is larger than what level? On level alpha, if the test statistic is larger than or equal to the critical value of standard normal distribution. Okay. If we take a look at the picture, here we have a distribution which fulfills the assumptions, and we take a look at how many blocks there are which are consecutively above or below the expectation, and we compare them with the expected number of blocks, standardize them, and find out whether this number of blocks, consecutive blocks, is sufficiently far away to warrant rejecting. Now, let's take a look at how this works on the concrete problem. Exercise 6.3. Suppose we have tossed a coin 20 times and we have obtained that sequence. suppose we have encoded heads as 1 and tails as 0, and we got 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0. And we want to test whether the results forming the sequence are independent. Okay. Using this test. Okay, now let's take a look. We need to separate the blocks which are above and below the expectation, meaning that we just need to count how many consecutive ones and consecutive zeros there are. So this is one block, this is another 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 block, this is a long block, this is a long block, and this is a long block. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 blocks not crossing mu. Good. So the test statistic, which is n minus n plus 1 over 2 over square root of n minus 1 over 4, is 12 minus, and no, 20 plus 1 over 2 divided by square root of 19 of 20 minus 1 over 4. Put it in a calculator and obtain that it is 0.68. Okay. The critical value of the standard normal distribution is found pretty simply. The z alpha half is, well, z 0.025. Here we have two options. We can either take a look at t 0.05025 with infinite degrees of freedom, or we can take a look at the inverse of the distribution function of the standard normal distribution, so it doesn't matter whether we use the table for the student's t distribution, look at the last line, or whether we use conversely the tables for the value 0.975. We just get 1.96. Okay, and if we just draw it like this, here we have the test statistic 0, here we have 0.68, and the critical region is either here minus 1.96 or there 1.96. So in this case, what do we do with the hypothesis of independence?
We accept it?
Yes, we do not reject the hypothesis of independence. Okay. Now, this means that in this sequence of ones and zeros, basically, we do not have the means of predict the next value. The next value in the sequence is sufficiently unpredictable. Now, what would happen, that's part C, if we would have a sequence of alternating bits? Would this sequence pass the independence test? It would not, right? You can guess one value from the others, and you can think that we have 100 of consecutive blocks. Okay, because well, each number is just on the opposite side than the others around it. So we have 100 blocks, and the statistic is, I will just write it down immediately, 100 minus, and now I have 100 plus 1 over 2 divided by 100 minus 1 over 4 square root of that, which is 9.95 And if we take a look at this, here we have the minus 1.96, here we have the 1.96 critical values and critical regions, and this 9.95 is way over there. So we do reject the null hypothesis. In this case, we reject it in favor that there is a dependence in the data. Make sense? Now, part D asks us what would happen if we would take blocks where there will be 10 times 1 and 10 times 0. How many blocks would we have then?
2. Oh, 10, okay.
We have 100 values, and at each point we have 10 times 1, then 10 times 0, 10 times 1, 10 times 0.
So 10?
10 blocks, right. And the test statistic is, well, 10 minus 100 plus 1 over 2 over 100 minus 1 over 4, which is I have it here, minus 8.14. Yeah, in this case, the test statistic was larger than the critical value, and in this case, it is the same. Yeah, the absolute value of the statistic is larger than 1.96, which is the critical value. So we also reject on the level alpha is 5%. So in the part above, the generator is bad in that way that it alternates the bits too much. And in this part, the generator is bad in the way that it does not alternate. It keeps the bits and changes not often enough. Make sense?
Yes.
Good. Now, could we imagine a sequence which would fool this test, which would be completely deterministic, but would fool this test into thinking that the data actually forms an independent sequence?
Okay, so in the first one we had 12 blocks for 20 bits, so we can try to do some kind of sequence that aims for the same number of blocks in also 20 bits.
Mm-hmm. Now, if you take a look at the test statistic, the test statistic is the number of blocks minus n plus 1 over 2 over n minus 1 over 4. If you take n as fixed, then to make the statistic the smallest, you would need to take the number of blocks closest to the expectation. So basically closest to n half. Yeah, n plus 1 half or n half, that's about the same. Okay, so for the sequence to pass the test, we need n close to n plus 1 over 2, and for n being 100, we have n plus 1 over 2 is 50.5, so we need about 50 blocks. So basically we need half as many blocks as we have observations. How can we do that?
It's 1 1 0 0 1 1 0 0.
Yeah. Then the test statistic is, well, there we have 50 blocks, 50 minus 100, 100 plus 1 over 2 divided by 100 minus 1 over 4, square root of that, which is pretty small. This is, well, minus 0.1, okay? And the absolute value is pretty much smaller than the critical value. So we do not reject independence. So even if this sequence is completely deterministic, 1 1 0 0 1 1 0 0, you immediately, if you have 2 bits, you can immediately say what is the rest of the sequence gonna be. This test is not able to find this. Okay? this test does not detect that there is a deterministic, well, ordering in the sequence, deterministic algorithm. So this test is sensitive only to some extent. Okay? That's why there is a whole battery of tests, each of them testing a bit of a different thing. In the lecture slides, you can take a look at a different test, which tests consecutive counts, not blocks above and below the expectation, but counts blocks of monotonous values. So blocks of where the values are either, well, this works on continuous distributions. Blocks which are either increasing or decreasing, and counts how many of them are there. And again, it was shown that among n values, if they are independent, there should be about 2 times n minus 1 over 3 blocks of monotonous values. So this plus this minus 1 times monotony changes, and the number of monotonous blocks has again a normal distribution, this time with different parameters. This is nothing which you would need to remember, just that there exists such a procedure and is one of many tests which can be used. And again, if we take a look at the number of monotonous blocks, here we have one block, there is a second monotonous block, third one, fourth one, compare it to the expected number of monotonous blocks divided by square root of the variance, we get something which is a normal distribution, and we can find out whether the number of blocks in the actual data which we have is far away from the expected number under the hypothesis of independence to actually for the sequence to be independent. Now, those are just examples of possibilities how to test independence. There are more tests which are, well, even more sophisticated. These ones are the most straightforward. Basically, where we immediately see how the quality of the generator is assessed. That you shouldn't be able to guess the next value from the sequence before. Does it make sense? Okay. So this would be all for the chapter of testing. Before we conclude this chapter concerning statistical methods and move on to the next part, we will just shortly see how we can do graphical estimation of a distribution's shape. Now, we have seen how to estimate parameters of distributions. We have seen how to find confidence intervals for parameters of distributions. We have seen how to test what can be their value, but oftentimes we have made the assumption that the data comes from a normal distribution or some other. If you get a pile of data in front of you, which you think that comes from a continuous distribution, you would maybe like to visualize them in some way to tell you how the data behaves. The most simple way of visualizing the shape of a distribution is taking a look at the histogram, taking a look basically at the proportion of data points which lie in individual parts of a real line. Now, based on top of this, there exist plenty of methods which can be used to estimate densities, estimate distribution functions, basically take the data and lead you to an assumption that comes from a concrete distinct distribution. There is a book from B.W. Silverman which covers most of the commonly used ones, and we will just go through several ones. One of them which you have seen on the bachelor's course, which you got before, or on graphs, which I have actually shown you, is the histogram. Now, the histogram is an estimation of a density of the distribution, and basically takes observed data and counts how many there are in individual fixed chosen intervals. And then it scales the number of observations in the individual intervals to produce a function which integrates to 1 and gives us the idea how the data is shaped. So looking a bit like this. Okay, so we have observed, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points, and we want to visualize how their distribution looks like, at least roughly. So what we do is we split the interval on which the data is being observed into some distinctive subintervals. Here it was pretty simple. We have just taken integer values, so from 2 to 3, from 3 to 4, and so on. Then we have taken a look how many of observed data we have in each of those brackets. And we have plotted a column of the size of how many there were, the data points, and scale it to integrate to 1. So basically, we divided the number of observations in each of the brackets by the total number of observations and by the length of each bracket. And this way we get a function looking brackety. It's not smooth, but it gives us an idea on what is the probability that a value lands in each of the intervals. Okay, so now you recall the density is such a function which, if you integrate between 2 points, let's say A and B, gives you the probability that the random variable in question will be between A and B. Yeah, this is this integral. And the histogram is the empirical version of this. Basically tells you that the probability that the new value will be between, let's say, 4 and 5 is given as the proportion of values which are between 4 and 5 to the whole number of values scaled by the length of the bin. Okay, so the probability that the value would land between 4 and 5 is, well, 4 out of 10. Okay, which is the area of this bracket. Now, the histograms serve for a straightforward, simple visualization of the data. They are not smooth. They depend on the length of the bins. and just give us a rough idea how the data behave. Make sense? At some points, we might want to estimate not the density, but the distribution function of the data. Now we know that the distribution function is the probability that the random variable will be less than or equal to value of x. And this is the integral of the density up to x. And now, if you take a look at this graph, and somebody would ask you what the distribution function, what would be the estimate of the distribution function, let's say at 0.5, and you would think about it for a while, you say, okay, so if I insert 5 here, they want me to estimate what is the probability that the variable will be less than or equal to 5. Okay, now this estimate is also pretty simple. I just look at how many points there are below 5 and compare it to the whole number of data points. Okay, so below 5, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 points. So my answer will be that the probability that the variable will be less than or equal to 5 is equal to 9 over 10. And this is what I am then able to give for any of the real numbers. So, and this way I obtain the so-called empirical distribution function, which basically at a concrete point x gets you the number of observations which are less than or equal to x over the number of whole, of all of the observations, so over the whole sample size. And looking at this exercise, going from the left to the right, the probability, the estimated probability that the random variable will be 0 or less is pretty simply 0. The probability that it will be this or less is equal to 1 over the number of observations. Then less than or equal to this is again the same. And going to right, we just keep adding and adding 1 over 10 until we reach 1. So this is the empirical distribution function. Both the empirical distribution function as the estimate of the actual distribution function, or the histogram as the estimate of the density, can be called in any software which has some inbuilt statistical functions, in Python stats, or in R, or even in Excel. There exists, not for the distribution function, but for the histogram, it exists a function which can plot it for you, and it gives you a reasonable first glance on the data which you have at hand. Let's take a look at a simple problem. Suppose we have counted how long did it take every morning until a bus comes on a bus stop. We have done this repeatedly 15 times, and we have measured the following data. We've ordered them to work with them simply, and we want to find the histogram and the empirical distribution function. Now, the histogram can be in R summoned by the command hist, HIST, and we need to scale it to represent probabilities, not frequencies. by adding the parameter probability is true. And we need to specify, or we do not, but we can specify how many breaks do we need, how long should be the bins be. And in this case, we have experimented with the data. Here we have chosen the bins to be equal to 1. So we have taken 12 bins on the interval. So the histogram looks like that. Then we have taken just 2 breaks separating the data point. We have the data points into 3 categories from 0 to 5, 5 to 10, 10 to 15. And at the end, I have just let the software choose for me. It chooses to make the fields to be exactly long 2 minutes. And now here we have the number of observations in each of the bins divided by the length of the bin and the number of observations. Each data point then constitutes the corresponding amount, the histogram. So looking like this. And if we would fit the curve of the exponential distribution in there, we would see that it fits pretty nicely. Well, because I have generated the data from the exponential distribution in the first place, but that's beside the point. The histogram gives you an immediate, simple look at the data. It tells you whether the data looks like uniformly distributed, or whether it looks like normally distributed, or whether it looks like exponentially distributed like this, or even following a different distribution. Now, the problem is, as you have seen on the last pictures, that we need to be careful with the selection of the bandwidth of the size of the individual brackets. If you use an inbuilt function in a software, it often has some pretty reasonable default setting, so that it looks most often pretty nice. At some points, I have seen in Python that the histogram might be the bandwidth a bit small, so then there are just such teeth which needs to be rectified by just selecting larger intervals to make a bit of a more smooth plot. Now here we see the empirical distribution function giving us the estimate of the probabilities. We see that there we have 15 data points. Each of them constitutes a jump of 1 over 15, producing us a partially constant stepwise function. In R, it can be plotted applying the function plot on the ECDF function. That's the empirical cumulative distribution function. If you'd like to, if you encounter a problem requiring you to plot it, you can do so. And then use it simply to estimate the probabilities. Now, for example, if we would like to estimate the probability that we would need to wait for the bus for 6 minutes or less, then we would just take a look at the functional value, which is just the number of observations which are below 6. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. over 15. So pretty straightforward estimate. Okay. Now some distributions. Now before we continue, does this make sense?
Yes.
Okay. Whenever you need to use histograms or the empirical distribution functions, you can refer to those slides. Now some of the distributions feel like they are not one of those which we have seen so far. Now somebody has measured the distribution of the lengths of the eruptions of the Old Faithful geyser in the Yellowstone National Park in, yeah, that's Wyoming, US, I think. And the histogram looked like this. Now, yeah, those are the durations of eruptions. It has been pouring water out of the ground, sometimes for around 2 minutes, and sometimes for around 4 or 4.5 minutes. Almost at no point it was between 3 and 3.5. Now, how does it look like for you?
Like two different distributions.
It looks actually like a mixture of two different distributions, right? There might be some procedure underneath the ground which at some points flows the water from one set of tunnels and then it pours for a short time. At some different points, it just connects to the geyser from a different set of tunnels, and then it erupts for this amount of time. This is called a mixture distribution. With some probability, you get a value from this part, and with some probability, you get a value from this part. In this case, it might even seem like this is akin to a normal distribution, and this, well, probably not, but it can be taken as a mixture of such two distributions, which we will get to. Now, at some point, if you are tired of brackety histograms and would like a nice smooth estimate of the density, what you can do is use so-called kernel estimate, which works in a way that, again, is pretty simple to visualize, but pretty hard to prime correctly and use correct parameters. Suppose you have some data points here, there, over there, and over each of the data points, you draw a Gaussian curve. And then suppose that you add them all together at each of the points on the real line. So basically, on this point, I will be just adding this value and this value. At this point, I will be adding this value and this value. And what would I get is a function which is at the end smooth and has a nice Gaussian hills and represents the proportion of data points in each of the parts of the real line, but with a nice Gaussian smoothing. Formally, kernel estimate works like this. At each of the data points, x1 up to xn, you plot such a function which is taken as, which is called a kernel function. It can be chosen either as Gaussian or different, but a smooth, nice function. You scale it a bit, you add these functions all together and scale them by the number of observations and the original scale of that function to match out the variances and to produce a result which at the end integrates to 1. A kernel function can be chosen as any function which integrates to 1 and is non-negative, basically any function which can be a density. And you need to choose how tight or how wide do you need the individual parts to be, whether you want above each of the points to have just one simple peak, or whether you want to have a large wide peak. That's governed by this parameter h, that's called the bandwidth. And it can be shown that a function which is taken as such a combination of these small functions integrates itself to 1. That's pretty simple using this property, taking some and doing a substitution in the integral. That's pretty simple to show. And here we see how this works on the exercise from the beginning. We have 1, 2, 3, 4, 5, 6, 10 values, and above each of the values we draw a Gaussian hill, and we combine them all together. Now, there are plenty of ways how the kernel can be chosen. One of them is Gaussian. One of them is Japanechnikov, which is not a Gaussian curve, but a polynomial curve. 1 minus u square, which is basically, well, square function looks like this. 1 minus square function looks like this. So it integrates to 1 instead of giving and multiplied by something so that it integrates to 1. And instead of such hills, it gives you such hills. It can be shown that this also makes sense and produces reasonable graphs. And most of the time they are pretty similar. And what matters is the choice of the bandwidth, whether you take the individual functions to be tight or wide. It was even, if you take, it would take a large value of the bandwidth and you would get flat, wide hills, you would get a pretty over-smooth estimate. If you would take the h to be pretty small, you would get it more raggedy. And it can be shown that there are several ways how to find a optimal way how to choose the kernel. Sometimes we want to minimize the mean integrated square error between the kernel. So expectation of the integral between the kernel estimate and the actual density. And it was shown that so-called Silverman's kernel, which is 1.06 times the standard deviation times n to the power of -1/5 is the optimal selection of the bandwidth, which is inbuilt in the functions producing kernel estimates by software, often as the default parameter if you don't tweak with it, as in one. Yeah, here is how it looks like if we want to find the kernel estimate in R for the data with the buses. The kernel estimate is obtained using the function density, and it is then plotted by the function lines, and the adjust parameter tells us by which factor should we scale the optimal bandwidths. So it takes the optimal bandwidth and forces you to multiply it by something. So here I have multiplied it by 1/2, and we see that I got an estimate which is a bit raggedy. If I multiply it by 2, I got an estimate which doesn't tell us pretty much because it is too smooth. And if I just use the optimal setting, it produces a pretty reasonable estimate, maybe with not taking into account the fact that the distribution starts at 0, right? Because the Gaussian curve, well, goes from -infinity to infinity, and it is not well bounded from one side, but it again gives us some idea how the data behaves. Okay, so this is how we can find, aside from the histograms, which are pretty simple to compute but are brackety, this is how we can find smooth functions to estimate the densities. Okay, the kernel estimates taking the functions and adding them together over each of the data points. Now, let's take a look how this works for the Old Faithful data. We have seen, here we have seen the histogram. And if we apply the kernel estimate, we see it basically looking like a mixture of two Gaussian distributions. Okay? And to conclude, at some points, it actually makes sense to work with Gaussian mixtures. It is the basics of some machine learning methods to think about data as a mixture of two Gaussian or more Gaussian curves. As we have seen on the Old Faithful data, it seems like pretty well separated two Gaussian curves, and theoretically we can establish such a distribution as taking densities corresponding to Gaussian distributions with concrete parameters and taking their convex linear combination. So if we think that the distribution has one Gaussian form with a probability P1 and another one with a probability of P2 and so on, what we can do is take the densities, multiply them by the probabilities with which we think that they are actually occurring and add them together. And this way we obtain a correctly defined distribution, which is actually called a Gaussian mixture. Now, this mixture has, if we take the probabilities as unknown, it has quite a plenty of parameters to estimate. For every part of the mixture, we have mu and sigma square as parameters, and then we have the probability with which it occurs, which we need to estimate from the data. The probabilities add up to 1, so we have one less parameter from the reasons which we have seen. There are ways of how the estimates can be obtained. One of them is the maximum likelihood method, which is pretty hard because of how the parameters are all mixed together, some of them representing probabilities, some of them representing the parameters of the distribution. A better way to estimate the parameters is the so-called expectation minimization, or EM algorithm, which we won't be going down to, but you can take a look at how it works in the literature. It basically iteratively estimates at one point the probabilities, at another point the parameters of the Gaussian distributions, then it moves forward, again estimates the probabilities more precisely, then again the parameters, then again the probabilities, then again the parameters, until it converges to something. And for the Old Faithful, we can assume that those are two Gaussian distributions at work, one occurring with probability p, and the other one occurring with probability of 1 minus p. And if we run the algorithm, it gives us two distributions, distribution 1, distribution 2, and with probability 0.35, the algorithm tells us that we will have the eruption falling in here with the expectation of 2.2 minutes, 2.02, and with probability flipped, so 0.65, the complement, we will have this thing with expectation of 4.28 minutes. Okay, so this is another way how we can work with data. You can imagine that, for example, if we are observing the height of people, you can imagine that men have a Gaussian distribution centered on, let's say, 180. Women have a Gaussian distribution centered on, let's say, 170 or whatever, I don't know right now. It varies from country to country. And all together, they produce one big Gaussian distribution. And based on some machine learning algorithms, you can, if you get a measurement of a height of certain person, you can then, by doing some reverse calculations and working with conditional probabilities, you can assign a probability that this person actually is a man or is a woman based on the height. This is called the naive Bayes method. Maybe you have heard about it. This is pretty straightforward machine learning method of using the Gaussian mixtures to reversely predict to which of the individual parts did the actual measurement fall. Now, in this case, it is pretty straightforward. They have almost no overlap. But in the problem with people, you can see that there will be lot of short men, there will be a lot of tall women, and based on just the measurement of height, you can just make some guess with some degree of certainty. Okay? Does it make sense?
Yes.
Good. Now this part regarding the estimations of densities is something which wouldn't come up on the final exam. It would be too hard to do on paper. You can use parts of this when working on your homework if you decide to do it, but won't be on the final test. Now, at this point, we have concluded the chapter concerning hypothesis testing, concerning statistical methods. It doesn't make sense to start the new chapter at now, so if you're okay with that, we'll just call it a day.
Okay.
And
What's next chapter about?
the next chapter will concern the random processes. We will start dealing with random processes. First, in the first 2 or 3 weeks, we will deal with random processes measured in discrete time, as in today it is sunny, what's the probability that tomorrow it will be sunny, and so on and so on, or at this hour the machine is working, what's the probability that after an hour it will be also working, or that it will be broken down, and so on. And then we will move to processes which are measured in continuous time, and we will stay by those until the end of the semester. Okay, so those are the last 2 major parts: discrete time and continuous time random processes. Okay.
Okay.
Now, just a quick reminder, the deadline for the quiz 1 is on Sunday, yeah. And quiz 2 concerning statistical estimation, well, not this, but what we did today and last week, is up until, I think, April the 10th.
Yes.
So you have again plenty of time to try that, but I suggest you try that if you have it, when you have it in your head, before you forget all about that. Okay?
Yes.
Good.
Also, I finished emails too, and I couldn't down one question. I got one question wrong, and I wonder why it was wrong. Can I ask you?
Okay, let's take a look at it. I will just stop the recording and we can directly take a look. Okay, stop recording.